Thank you very much. Thank you. First of all, thank you very much to the organizers for the invitation to speak here. It's been a wonderful conference so far. I'm really enjoying it. And it's my first time in Korea, so thank you for that opportunity as well. So I'm going to talk a little bit about an idea that I've been thinking about for just over a year now, I would say. And this is the idea of positive integrands in the Minkowski regime. And I'll explain what I mean by that concept as we go on. And this is some work that I'm about to publish with my PhD student, Thomas Stone, and the PhD student of Gudrun Heinrich, Anton Olsen. And I'm also developing these ideas with the rest of the PySecDec collaboration. And I'll bring in some ideas from some earlier works that I had with Inan Gardi and Franz Herzog, Yama. Okay, let's get started. I think we are not focused. Yeah, perfect. Okay, so I'll start the talk with a little outline of my interests. So why am I interested in this type of problem? And my background is precision collider phenomenology. So I'll say a few words about some of the state-of-the-art calculations there before moving on to the sort of main topic of the talk, which is just revisiting how we compute things in Feynman parameter space, in particular from a numerical perspective. And I'll focus in on this idea of contour deformation and some of the problems this raises when we try to compute integrands in Feynman parameter space, and then introduce this idea that I've been working on. Okay, so a lot has happened since the last Amplitudes conference in the world of collider precision, I would say, as always. And one of the measures of this is the updated Lezouche wish list. So every 2 years, people meet in Lezouche, France, and they look at which processes are interesting from a theoretical perspective, as well as from a collider experiment perspective, and draw up a list of sort of the latest fixed order predictions for processes involving, say, Higgs bosons, jets, vector bosons, top, etc., as well as a list of desired predictions from either the experimental or theoretical perspective. So this is kind of collaborative effort between the two fields. And here I've just stolen a few tables from the latest update and just highlighted in green processes that were either completed in the last Lezouche cycle of 2 years or where significant progress has been made on desired processes. It's fair to say that despite venturing into increasingly difficult territory, the progress is still steady and quite impressive. And people are just battling these calculations. So there's plenty of inspiration there. And I'd also say, since this is a collaborative effort, if you think that certain processes of interest, either theoretically or experimentally, are being overlooked, then absolutely get in contact with the conveners there, suggest things, get involved in the process. Recently, sort of the main motivations, I would say, for adding processes to the desired column of this wish list were either the upcoming high luminosity LHC, which is obviously going to reduce statistical uncertainties, but also systematic with that. And that means that there's a strong demand for very precise theoretical predictions to make the most of that data. But in addition to that, there are also theoretical issues that need addressing. So things like mass uncertainties and so on, where theoretical calculations are available in certain approximations, and it's interesting to explore how valid are those approximations. So I'm just going to pick 2 highlights from this list where I think very interesting results have recently been published. So one is the virtual amplitudes for Higgs plus jet at 3-loop. And this was published quite recently by Bernard and his collaborators. And here they worked in this so-called generalized leading color limit. So it's not the complete calculation, even within this framework of the heavy top limit. So they work within an effective field theory where you integrate out top quarks, essentially, which means that you now have vertices between gluons and the Higgs boson, which simplifies the calculation significantly as you no longer have these massive tops running all over the place. And this is a very good limit to take, especially when the invariant mass flowing through this is below the threshold of the top mass. So even within this effective field theory, they looked at the leading color, including also NF contributions. And this is a very, very impressive calculation. They point out in their paper that one of the bottlenecks, so sort of one of the areas where input from this community would be greatly appreciated and was greatly appreciated, is in the integration by parts integral reduction. This is extremely challenging for processes like this. And they finally achieved this using the BLADE program. I suspect a private version of the BLADE program with the latest innovations, as well as various techniques that have been developed in the literature, like improved seeding of the IBP system and so on. For the master integrals, again, a great challenge. They have 3-loop massless integrals with 1 off-shell leg. So this is state of the art in some respects, I would say. And the planar and non-planar results were expressed in terms of GPLs. So I would say from the perspective of this community, this is a relatively nice result in the sense that it's analytic. We can obtain more or less as many digits as we would like for this. And many of the sectors had appeared in the literature earlier and were computed by members of the audience, with 2 remaining sectors that they had to attack to complete this calculation. It's worth noting that further topologies are still required to obtain subleading color, so there is still more that can be done in this direction, but I think this is a very impressive landmark calculation. Another calculation I'd like to mention, which takes quite a different approach in some respects, are the 3-loop corrections to Higgs production, including 2 different quark masses. So now we're thinking of diagrams like this, where we have an internal massive B quark and an internal massive top quark. And this was performed by the group sort of surrounding Chacon, and also Marco contributed very strongly to this, Johanusovic as well, with the virtual amplitudes. They've looked at this in the on-shell and the MS bar scheme for the quark masses. So you can start asking questions like, how does perturbation theory behave when we renormalize masses in particular ways? So in order to actually compute this thing, they used a combination of asymptotic expansions. So this is expanding in a particular limit in the masses, as well as sort of, I'd say, semi-analytic approach based on AM flow. And here you see that it's still very useful from a physics perspective, from getting predictions for colliders, to be able to approximate these or expand them in interesting limits. And there's a lot of value in the technology and the ideas behind that. To give you an idea of the sort of results that they obtained, here we have the difference between, say, MS bar scheme and on-shell scheme for the top contribution to this. And at next to next leading order, there's a rather small correction, the difference between these 2 mass schemes. And so we would say this is converging very nicely. It doesn't matter terribly which mass scheme you pick for your top quark at next to next leading order, because you have enough orders in the perturbative series that it doesn't matter so much. It's slightly different if we look at, say, the top-bottom interference. So there, if you work in, say, the on-shell scheme, you see that the correction at next to next leading order is quite large and similar in size to the NLO, but with opposite sign. So you see that the perturbative series doesn't seem to converge particularly well in this mass scheme for the bottom quark, whereas doing this in MS bar, you get much smaller corrections at next to next leading order for what it's worth. And this is very interesting because it addresses one of the largest remaining uncertainties on this process if I ignore the scale uncertainty and the PDF uncertainties. Okay, so for the main part of this talk, I'd like to sort of revisit some of the basics and tell you about this idea of getting positive integrands in the Minkowski. And this is part of a program of numerically computing Feynman integrals that I've been involved in for many years. So as we all know, we can go to parameter space, so we can exchange our integrals over loop momenta for integrals over so-called Feynman parameters. We obtain our beloved formula. And there are just a few things that I need to make sure that I highlight and sort of set out my notation here. This is written in terms of 2 homogeneous polynomials of degree L and L plus 1, where L is the number of loops, so U and F polynomial. It's a projective integral, so you have to integrate this over the positive projective simplex. Or one special case of this is that when we have our delta function by the Cheng-Wu theorem, we have some choice of the hyperplane that we use to bound our integration domain. So this is one way in which this projective freedom shows up in this parameterization. Okay, and of course, there are many different ways of parameterizing Feynman integrals. They all have their different uses. For example, Lie-Pomeranski parameterization is very interesting in the concept of in the context of the method of regions or expansion by regions. And we've had several talks at this conference about the power of Bykov and loop-by-loop Bykov. But I'm going to focus on this Feynman parameterization. So if we look at this integral, it has a kind of elegant simplicity, I would say. A few things that we can notice. The UV and IR singularities of this integral come when some parameters, some x's, go to 0. So some subsets of these x's go to 0, or they can go to infinity, it's projective, simultaneously. So from this form, we can extract, if we want, UV and IR singularities, just looking at the parameter integrand. Another feature is that there are thresholds when the f polynomial vanishes inside the integration region. And there we have this I delta prescription that is the causal Feynman prescription. So it tells us that when our f vanishes inside our domain of integration, how to analytically continue, or how to go around the poles on the real axis of our parameter integrals when f vanishes. And this is sort of the main topic that I'll discuss here. Let me first remind you how these polynomials look. So we have the U polynomial, which we can construct just by looking at the graph. You just cut L loops such that you obtain a tree in every possible way, and you write down the Feynman parameters associated to any propagator that you have removed in order to obtain this tree. For the F polynomial, it's similar. You look at ways of removing L plus 1 propagators such that you obtain 2 separate trees. And then this comes with a prefactor associated with the momentum that would flow across the cut that you've made. The F polynomial, in all generality, can also receive a contribution from a term like this that's proportional to the internal masses of the process. And what's important about these polynomials for this talk is that both U and F naught polynomials are linear in any given Feynman parameter. And then when we add our mass terms, they can become, the F polynomial can potentially become quadratic in the Feynman parameters. Nice and simple. Now, the signs of the monomials in this F polynomial, they depend on kinematic invariance and masses. So that means that in principle, this polynomial can have monomials with different signs. If we think of a particular kinematic point, a particular phase space point, or a particular arrangement of masses, then our F polynomial has monomials with different signs, and these monomials can potentially cancel each other. So let me set up some sort of notation or some way of naming these things. So if all of the signs are the same, I would say that this is a manifestly same sign regime. And then the F polynomial can only vanish when subsets of the x's go to 0. I don't need to worry about monomials canceling each other and causing me difficulty. If f is just positive when my x's are positive, this is also a same sign or Euclidean regime. So in principle, the individual monomials might have different signs, but as long as I can show that in the positive orthant, f is positive, I'm Euclidean, everything is good. There's also a region where there's also an arrangement for some integrals where f is always negative in the positive orthant. And this, I would again say, is a kind of same sign regime for the f polynomial. It's always negative. And we could call this maybe pseudo-Euclidean. So f is always negative. Otherwise, we end up in the more general case where we have mixed signs. There are parts of our Feynman parameter space where f is positive and parts where it's negative. And if we think for a particular value of our kinematics, so we fix our s and n's, then the equation f equals 0, so the point at which f changes sign, or the variety of f, defines a codimension 1 hypersurface within our n-dimensional parameter space. Okay, this brings me to the concept of the Landau equations. They've been mentioned several times in this conference, and of course, a very interesting topic in their own right. So the Landau equations give us a necessary but not sufficient condition to have a singularity of our integral. And they can be written in terms of f equals 0, as well as x times the derivative of f equaling 0 for all of the Feynman parameters. And we say that we have a leading Landau singularity if the second equation is satisfied without any of the x's being 0. So it's really that each derivative is individually 0. This we would call a leading Landau singularity. And we can again think of solutions or leading solutions of the Landau equations as pinched surfaces. What do I mean by that? I mean, these are surfaces on which several hypersurfaces defined by the derivative of f being 0 intersect. So you can imagine each of these derivatives defining some hypersurface in your space. There's maybe for some integrals, there is a special point where all of these surfaces intersect. And then we would get a leading Landau singularity. And the study of the Landau equations is a very, very rich subject. It's led to ideas like the method of regions, how we can expand the integrals, how we can understand singularity structures, Landau discriminants. This is helpful for deriving, say, symbol letters, etc. It's interesting in the context of unitarity cuts, discontinuities, and so on. And we had a talk yesterday by Felix about solutions of the Landau equations. And you can probably insert many, many more topics there that are related to this. So then I asked the question, so what happens if we only satisfy the first of these equations? So we're not going to get a singularity of our integral, but we could still satisfy just this first equation and not the second equation. And I'd like to consider that in the context of direct numerical integration in parameter space. So as we really want to just Monte Carlo sample these Feynman parameters, or quasi-Monte Carlo sample over these Feynman parameters. Well, this leads us to the concept of contour deformation. It's not so straightforward to do this if we can satisfy that first equation in the physical domain that we're in. So what we do, if we take a look at our Feynman integral after we integrate out our delta function, we can restrict ourselves to the hypercube by a judicious choice of how to integrate out that delta function. And we have some equation like this, some integrand like this, where the I delta prescription is very important now because it tells us how to continue around poles. So the obvious thing to do here would be to integrate between 0 and 1, ensuring that we go around the poles in the correct way. But if we actually want to do these numerical integrations, approaching this pole is not a smart thing to do, where we'll have very large cancellations potentially. Our integrand will have very high variance. This is not necessarily what we would like to do. So instead, we can use Cauchy's residue theorem and say, well, we can swap this contour instead for some arbitrary contour where we stay further away from this pole, provided the loop formed by these two contours doesn't enclose a pole. So we need to explicitly pick a contour if we want to numerically integrate this thing. And the solution of how to pick such a contour that makes sure that we go around these poles in the correct way was worked out in 1999 by Davison. And the idea is the following. Well, if you, instead of sampling f on x, a real parameter, you deform each of your parameters into the complex plane. So we now have a complex integrand. And then you think about expanding f of z around x. So for a small imaginary part, then this is just a simple Taylor series. And then you'll see that, okay, this tau that we've introduced here, the small imaginary part that we've added to our Feynman parameter, if we choose this to be proportional to the derivative of the f polynomial, then for some small enough set of lambdas, this expansion will converge. And if we plug this into here, we'll get a term that's proportional to the derivative all squared. And this means that we can ensure that we get a negative imaginary part if we deform in this way. So this gives us an explicit way of picking a contour that we can be sure has the correct imaginary part and respects this I delta prescription. And so we can find these contours. In general, we could just take these lambdas to be any function. So you could pick just constants, which is often what is done. But you could also generalize this lambda and say it's some function of the Feynman parameters. And you could do something like train a neural network to try to optimize the choice of this lambda. And this is something that we investigated, right? So picking this lambda, bit of an art form, is the takeaway message. So let's show an obligatory bubble integral example, which I think I've seen in, I don't know, maybe 50% of the talks in this conference. So let's take a look at how this looks here for a bubble integral. Say we have some massive bubble integral. We can write it like this. Then we can integrate out our delta. We now have some integration over some contour. And here I show you how this would look. So in the space of this complex variable z, we would naively just want to integrate between 0 and 1, but that would take us through these poles where f vanishes. So we can't do this. Our integrand would diverge, it numerically wouldn't work. So instead, we have to deform our contour, and we could pick, say, this red contour, and this is the correct prescription for how we should go around these poles, or we can pick, a much wider contour that keeps us much further away from these poles. That's this green contour. This allows us to dodge around these poles. And we can see by looking at the imaginary part of f, what these contours are each doing is pushing us such that our f always has a negative imaginary part. So it carefully chooses a contour such that we're always pushed in the correct direction. Now, a few things are not nice about this. It's quite arbitrary which contour I'm actually integrating along. And it's not so problematic for this integral, but in general, we would get some Jacobian determinant from this change of variables from real to complex. And this Jacobian determinant is an n-1 by n-1 matrix, where n is the number of propagators that we have. So this can grow quite nastily. And of course, it depends on the derivatives of the f. So it's a Jacobian matrix with entries that look like various derivatives of the f polynomial. Not so nice. Okay, so there are a few downsides to contour deformation. First is that our real valued integrand now became complex valued. Okay, this might be nice analytically, but numerically, this is just slower. So I'd prefer to avoid it if we can. We can get large and complicated Jacobians, they're just slow to evaluate when we go from x to z. Now we can optimize this by sampling it or computing it in a very particular and smart way using properties of the f polynomial. And Felix has been on a paper where they use exactly this concept. We might even be able to compute it without ever writing down an analytic expression for this Jacobian determinant using something like dual numbers. But there are other problems. So it increases the variance of the function because now our function can be both positive and negative, and we can get cancellations within the domain of integration. So numerical performance can be degraded by this. And there was a nice example of this in the context of phase space integrals that was published recently by Renee and collaborators. It's also arbitrary, and it's very sensitive to the choice of contour. So yes, we can contour deform, but what should the lambdas be? How should we pick the lambdas? It's a bit random. There's not really a very nice solution that I'm aware of. And perhaps biggest issue is that it sometimes just fails. So it can happen that there is just no way to do this contour deformation. And the easiest way to understand that is we're deforming proportionally to the derivative of f. If all of the derivatives vanish, i.e. we have a leading Landau singularity, we're not getting any deformation at exactly the point where f vanishes. So this is bad. So it can be slow, arbitrary, and it can fail. So this is sort of the motivation for how, looking at different ways of doing this. Now, I'm certainly not the only person to think about this problem. So there have been various efforts to avoid or mitigate contour deformation in numerical contexts. For example, in the context of loop tree duality, people have looked at this idea of threshold subtraction. So if we can work out all the thresholds of this, say in momentum space, and then we can get local integrands that exactly cancel this threshold behavior, we can create this kind of threshold subtraction. And this will allow us to compute this integral without any kind of contour deformation. And then there are more numerical approaches where we can say, okay, let's leave a finite delta, but try to make a change of variables that flattens our integrand near delta going to 0. Okay, the approach that I've been developing is a little bit different from each of these approaches, I believe. So if we return to our bubble integral and we think about this picture now in n dimensions, so in 2 dimensions for this bubble integral, n is the number of Feynman parameters, then the contour that we would naively want to take is this one, just goes straight through our poles. And if we look at this in the n-dimensional space, what we have is we have x1, x2, we have solutions f equals 0, They go through 0 because if we set all the parameters to 0, then f is 0. So you have these solutions. And then our delta function, if we pick it like this, constrains us to lie on this hyperplane. Doesn't matter which hyperplane we pick, but this is an example. So we're integrating along this line. And now these things are not really poles particularly, but they're more intersections between the variety of f and our integration contour. So I'd say these singularities kind of lie on the intersection of this boundary hypersurface defined by this delta function that we've picked and our f variety. So the idea is to construct transformations of the Feynman parameters which map f equals 0 to a boundary of integration for a given kinematic region. So we specify which physical region we are in, say above a specific threshold, and we say, well, we know where f is 0. If we can map this to a boundary, we can essentially split our integral up such that we integrate from our coordinate axes to f equals 0, and then integrate from f equals 0 up to our next coordinate axis. And for transformations which will make f non-positive, we can factor out an overall minus sign using the I delta prescription to generate the correct, causally correct imaginary part. And then we can stitch together the resulting integrals. So it means we can take an arbitrary Feynman integral and instead write it as some integrals that are manifestly positive in the whole integration domain, plus some integrals that are negative. We have factored out the minus sign from these integrals. So these integrals themselves now are manifestly positive. And the entire analytic continuation, all of the complex behavior just lives in this prefactor here, which we know how to evaluate. It's very simple. It's -1 to some power of the f polynomial here. And these individual integrals have real non-negative integrands. That means we don't need contour deformation. The analytic continuation is trivial because it's written explicitly in this formula. And these integrals are also faster to integrate in many cases, which I'll show you. Okay, so how do we actually do this in practice? Let's look at a first toy example. We can look at, say, a massless one-loop on-shell box. Very easy. The f polynomial is given here. And let's consider it in a kinematic regime where s is positive and t is negative. So this is a sort of physical 2-to-2 scattering kinematics. The problem that we have is that we want to find, say, the region where f is negative, where all of the x's are positive, and we're within this kinematic domain. Actually, doing this is very straightforward in this case. If we can solve this equation for one of the Feynman parameters, and it's linear in each Feynman parameter, then we will just get a limit on we'll get a boundary of integration for that particular parameter. So we just solve this equation for x1, easy peasy, and then we'll get this limit of our integration. And we can now bisect this domain in the variable x1. Now, in this case, I call it univariate bisectable because I just need to pick a parameter, solve it, and this splits me in two. I can map f equals 0 to x1 is 0 with one particular mapping, and this will give me what I call f minus. Or I can map f equals 0 to x1 is infinity with this relatively simple transformation, which depends on the boundary of integration, and this will give me f plus. So the resulting integrands will be a product of dimensionally regulated polynomials that are positive in the positive orthon of the Feynman parameters, homogeneous by construction because the transformations I've made are just chosen to be that way. And then we'll see that our integrands look something like this. We get a Jacobian from this change of variables, but it's often very simple. In this case, it's a univariate thing. Our U polynomial looks pretty weird, different from what we're used to maybe. And our F polynomial is essentially constructed to be very simple. Plugging this all together, our final Feynman integrand will look something like this in one of these sectors and something like this in the other sector. And these things are just positive things, right? We don't need any contour deformation. And then the final result for this box integral will be some gamma prefactor. And then it will just be a sum of these two integrals where the negative one just receives this prefactor, which will expand and give us all of our I pi's and all of the imaginary part. So we can turn this into a simple pseudo algorithm where we essentially just try to look if we can bisect our integral in a single variable. So we just kind of go around the loop, trying each variable, and then this tells us exactly which transformations we should make depending on the form of the system that we get. And this algorithm will either find this bisection if it exists in this kinematic region, or it will show that this integral can't be bisected in a single variable. Okay, so some examples of the types of integrals for which this works we've tried. So these are various univariate bisectable integrals. So we have massless boxes, also with off-shell legs, pentagons. We tried this also at 2-loop for 4-point functions, all massless, and even at 3-loop for 4-point massless integrals. This works very straightforwardly. Essentially no complication compared to what I just showed you. So just to give you an explicit example, if we take this 2-loop integral, this is maybe a little bit interesting in the sense that if we obey our momentum conservation rules, then there is no Euclidean region for this guy. We can again just follow the procedure. We will get our set of transformations, and then we will be able to dissect this thing and integrate it. Okay, next complication, masses. So I talked about the massless case. This F0 was linear in each of the x's. If we go to the massive case, it's now quadratic. It's very easy to encounter non-univariate bisectable integrals. The solutions for F generally contain square roots, and there are often more thresholds or more distinct kinematic regions. So returning to our first bubble example, we would see that we actually split into 3 different domains of integration now, not 2. So it's not bisectable in that sense. Region 1 and 2 are positive regions. And then between these solutions, F equals 0, our F is actually negative. And so this gives us a third region. But it turns out that if you just think about this a little bit, you can quite straightforwardly solve this, and you can still obtain a dissection of this, but now into 3 regions. That means that you can express this 2-mass bubble as a sum of 2 positive integrals and a negative integral like this. And I show you just the full result here. Again, the resulting integrands are positive and homogeneous. We also didn't make a particular choice of hyperplane in the resolution that we made here, so you can choose whatever hyperplane you like. We also can maintain symmetries of the integrals, so we see that these positive integrals are actually related by interchanging Feynman parameters and masses, and you can leave this manifest if you like. So some examples of massive integrals that we initially looked at, we restrict ourselves to 1-loop, bubbles and triangles with various mass arrangements, and these all go through. You can find the transformations without too much effort. So how about something a bit more interesting? Maybe we can go to, say, a 2-loop elliptic or a 3-loop hyperelliptic function. And here, if we take a look at our F equals 0 hypersurface, focusing on this 2-loop elliptic where I can actually depict the thing, you see that it actually looks rather like our bubble hypersurface in the sense that there are these solutions, but now it traces out a cone in the hyperplane as we intersect it. And so if we take a look at the intersection of the simplex with this solution, then you see that you would like to integrate inside this simplex here. There is a kind of cone inside there, distorted cone, I suppose. And inside this cone, your F is negative. Outside, it is positive. You can transform this back to a hypercube. And then, due to the symmetry properties of this integral, you can actually split this hypercube in 2. It's not essential for the method. It doesn't matter. Then you obtain some picture like this, where this curve here is the edge, one of the edges of this cone that I was showing you. This blue region will be negative. And then we can split the positive region up by just finding the roots of this ellipse and then splitting it up into 3 positive regions. Now, when we do this, the transformations are algebraic, so we will get square roots rather than polynomials. But the singular structure can still be factorized out. So we can still use standard techniques to actually sector decompose this and obtain the singularities of this. And we will get this as a sum over 3 positive regions and a negative region with the analytic continuation explicit. Now, carelessly integrating out the delta function doesn't give so nice results, let's say. And I think there are definitely better ways of doing this. But this is just a proof of principle that you can do this. So you take this elliptic integral, you factor the singularities out, and you have some finite regular remainder here. which is this very ugly function that depends on the kinematics and some of the Feynman parameters. But this satisfies all of the properties that I was demanding. So how does this actually perform? So we can look at the numerical performance of this. What we do is we can benchmark this, for example, using PySecDec. So we apply sector decomposition to the integrals. We use quasi-Monte Carlo integration to integrate these things up. And let's take a look at, say, this one-loop pentagon integral. And here on the y-axis, I show you the integration time. So this is sort of the Monte Carlo sampling time to get a single phase space point for this pentagon integral. Of course, you know this analytically. You don't actually need to do this for a one loop, but this process works generically, however many loops, however many masses. So it's useful in that respect. Then on the x-axis, I show you the requested relative error. So essentially the number of digits that we're getting correct. Say out here, we're getting 10 digits of this integral correct. What you see is with these solid lines, the time it takes to get a specific number of digits using contour deformation for this guy. Contour deformation will work. We can tune our contour. We can find a good contour. And then you'll see that if we go into extreme kinematic configurations, for example, if we make S12 very large, leaving the remaining Mandelstams rather small, we can drive ourselves into corners of phase space where the integration time is very, very high if we use contour deformation. So up here, more than 10 to the 3. It's very unstable numerically. But if we avoid contour deformation, then we're on this purple dashed line down here. You see that you can get results for this in a matter of seconds, many digits of this. So it's sort of speed ups of 10 to the 4, especially close to singular or pinched points. So this is promising because evaluating 5-point functions beyond one loop with SecDec was always quite challenging. And I suspect this is really the reason, right? There's nothing particularly new and difficult at 2-loop from this perspective. We can have a look at, say, this 2-loop example here. And again, these solid lines are with contour deformation, and these dashed lines are using the method that I described here. And you see, certainly if you want several digits of this, sort of 8 or so digits of this, then you don't want to be using contour deformation, where the times are 10 to the 4 seconds or something like this. So it's fairly difficult to evaluate with contour deformation, very, very easy without. We can have a look again at this slightly more complicated 2-loop example. And finding a contour for this is so difficult that we didn't really manage it in any reasonable amount of time. And yet without contour deformation, this thing is not terribly difficult. So this is a great improvement. We can look at some massive examples. And we see, for example, for a massive triangle, in the limit that m is small, our contour gets pinched because it would develop 1/epsilon poles. Whereas using this method that I described, there's no contour to pinch. So we have enormous speedups in this case. For the elliptic, I would consider this more of a proof that we can resolve this and evaluate it without contour deformation. But this is sort of less competitive, speedups of sort of 10 to 100 times for this type of thing. Okay, the final comment I would like to make on this is towards a more general picture. And the question is, can we always perform this procedure? What we're trying to do is find a sign invariant decomposition of this set of inequalities. And indeed, there is a technique in real algebraic geometry called generic cylindrical algebraic decomposition, which is exactly designed to solve this problem. And there are algorithms that you can apply that will solve this problem. The nice thing is that they're guaranteed to work and they're constructive, so they really do give you solutions. The bad thing is, like Rogner bases, they're doubly exponential in complexity in the number of variables. And they can potentially give you higher roots beyond square roots. However, we're interested in a rather special case. And in practice, we've observed that it's much, much simpler than the very generic mathematical situation. Last comment. We can apply these techniques to integrals of more phenomenological relevance. So going back nearly a decade, I should say, if we look at something like glue to di-Higgs, we can take an example. We can apply this CAD to this example. And we can see that we can obtain for the region between the di-Higgs threshold and the TT bar threshold speedups of sort of 10 to the 3 times in the numerical integration performance for this thing. So to give you an idea of where that puts us, if we look at the glue to di-Higgs amplitude at 2 loops, has 406 master integrals. If we just throw PySecDec at it with contour deformation, the time to integrate this for a single phase space point is around 90 seconds, let's say, using a modern PySecDec. If we apply this technique then we could be optimistic that this greatly accelerates this, allows us to go maybe beyond 2 loops or to higher point functions. I'll leave this slide, I think. It'd be interesting to have an interpretation of these things. That brings me to my conclusion. Thank you very much.